还有13分钟。
是什么意思
？open hour， 我们会有讲如何去做CPU take out 啊，或者 CPU take out。
太神了。
OK。
C'est un HDMI connector or the camera here?
No,
I mean from my
okay.
couldn't find my tissues. Frank, I'm the next one.
Yeah, you're the next one.
I will listen, and if it's good, maybe I'll even play.
Hey.
Make one shit.
Sorry, I really don't have it.
You have tissues, but I don't find the trash can.
The trash can. I don't know. I'm sorry.
No, I just talked with the guy, he said, yeah, go to the men's bathroom. That's where I'm coming from. It's only access time.
Yeah.
It's a long walk.
The long walk.
Oh, sorry.
I guess that. Okay.
There's one button. So you're coming? No, because you didn't invite me.
Yeah, but because they want to discuss more about the processing and stuff, and that's the reason why when we focus on the IGP, I do want to promote the design, so they are going to do the manufacturing, and the core and stuff seems to be too high level to that. I try to pursue, I really want to invite you, but you know, there are a bunch of bureaucracy. I think that maybe can talk a little bit about it. It's like a little bit back and forth, like it's like kind of.
No, I'm not talking this issue. It is also, I just was thinking, is how I never helped him in person, but I understand them.
Yeah, I mean, yeah, they even need to censor the question with some of the messages entry that is put like them. They are very, a bunch of people don't like to get to. I don't want you to use the word strangers, but they are very, I'm liking it very close. I really want to introduce you to them. It is mentally unable.
我一直都会听到这个觉得很文艺。
They make the call, they make the call, and you can remember that the math and those people I talked to the TSI like it's very long time. They say okay, they're okay with these guys. It's like they simply give you the orders to hey, I'm okay with this, I'm okay with that. It's not like they feel like the other way around.
They are not okay with me. Oh, I will complain to.
Yeah, if you really complain. I'm not sure why. I don't want to be a bad guy.
Okay, I don't bother you. Maybe you can give the card after the meeting. So we're 1 minute left to the talk that we are very fortunate to have a guest from Germany, and he will be talking about the open source PhD, just like the person that wrote to me. He said this is very, very rare because it's almost a trade secret for a foundry. So without further ado, let's welcome our friend Mayor from HP. Okay, thank you very much. Welcome to my talk. It's a follow-up from my talk in last year. So I will give you a short update and what's the current status and maybe what we'll do in the future. First, I'd like to introduce IHP itself because most of them won't know the IHP. Like this institute, we are the research facility for high-performance microelectronics, and we are located in Germany. And we are research and innovation center for silicon-based systems and ultra-high-frequency circuits and technology. And that's even the reason because we have this BiCMOS technology. I will later talk a little bit more about this technology itself. And we have a vertical research concept, so it means we have everything starting from material research to technology department also means the fabrication of the devices, continuing up to the system department, and on system level you can even create microcontrollers, high power processors, some different stuff, maybe using resistive devices for AI applications and so on. As you can see, we are more than 300 people which are working in RHP, and we get even additional support by students and so on, technical stuff. Everything what you need to drive such a large institute with administrative, and even you can see the clean room, also the picture on the left side. And this is even our unique selling point. So we have a 200mm pilot line for state-of-the-art BiCMOS technology, and this is even an industrial like style. So we are running 24 hours, 20 days, 7 days a week to produce prototypes and even volume productions. Our technologies are qualified, so it means you can even build your devices, for example, for measurement equipment and so on, and we have a qualified technology, so it means everything what you get is reliable under certain conditions. Our clean room area is roughly 1,500 square meters, and we have this specific CDG BiCMOS technology. And we have to. I don't know anymore. But we have two different technologies. One is the copper nickel technology, mostly used for image technologies, and the 130 nanometer technology, which is mostly used for applications. We have a type of circuit. This circuit shows you the dependencies between all the stuff that we have that are related to the open source, PDK, open tools, open designs. And you see a strong dependency between everything. Without the PDK, you cannot create the tools. Without them, you cannot even verify the designs and so on. And it's very hard to break the circle to start type of development for everything. Yeah? For example, you cannot develop a tool if you don't have the input from a PDK. And the second is, if you don't have designs for checking the tools, it makes no sense to develop it further. That's a little bit an overview about the challenges for the PDK development. So, as I said already, there's a strong dependency between the PDK, the tools, and the designs. So, how to start? Basically, the PDK is provided by the FEM. And I can say that the PDK is more than a process specification file and the design manual. Since I am the team leader from the PDK team in IHP, I can tell you that this is much more. Yeah? And one simple example, the files that we are providing in the PDK, that would be a MOS simulation model, for example, that has to be compatible with the tools. Second example, if you have a standard cell library, it has to be well usable. It's not enough to provide a standard cell library that works somehow. If it's not efficient, no one will use it because the processor is getting very large and maybe not reaching the stuff that you like to get, for example, the frequency and so on. For the tools, how do you get the tools for the open source designing? First, you have enthusiastic single person. For example, the NG-Spice is a simulator that is originally from Holger Code, he developed this. Then you have research activities of PhD students or funded projects. You have using now different, for example, the open Roadster hosting a large funded project. And even one challenge who maintains this after a certain time. Some people left, the PG students are ready, and it's also maybe as a Git, as a project in GitLab going to sleep. Yeah. And the last problem or challenge is are the designs. Just making a design makes no sense. You have a builder, it makes no sense to have just take a look onto the pretty nice picture if you have the layout and the schematic and so on. You will even get a real hardware. But finally the question is who can pay the design? Maybe you know it's relatively expensive to get final silicon. Luckily, for example, with the Google Sky Wonder, there's the possibility to get free samples, but mostly you don't have the possibility to verify finally your design in silicon. What might be the solutions? At first, you have to have the idea of the open source PDK itself. That sounds very easy, but you need this as starting point, the idea itself. Yeah? Without that, you cannot start. Yeah? Then, we were very lucky because we get some funding by a German ministry from BMBF. And finally, you need, of course, the people. Yeah, you need the ideas, you need enthusiastic workers, you need time for that, you need knowledge. Without the knowledge, it can be very frustrating, very you need deep collaboration. Without collaboration with other people, other research institutes, you cannot do it. Some words regarding the funding. We got the funding for an F&D QAC project. It's in the last line mentioned. And there are three main tasks. The first one is developing PDK. The second one is tooling and teaching. And the last one is open design platform. I will talk about each one separately. And new point is, maybe you can see it in the third line, we're supporting the free free area in our MPW shuttle runs. Finally, we like to push our German Electronic Academy with certificated design courses and design infrastructure using our open source PDK and tools. Some words about the open source PDK itself. Maybe you know the slide already, because I give it from time to time. At first there was a really internal discussion, it took a long time. Should we release an open source PDK? So finally we made the decision, yes, and then was the second question, which technology? So now 2 years ago on the F6 in Paris, we announced that we will release an open source PDK for our HPS G32 technology. And in the next slide you can see the technical details. So it's by CMOS technology with an HPT of FTF max of 350 450 gigahertz. And CMOS part with 130 nanometer technology. The first technical data were published in March 23 on GitHub. And there's a link if you want to use the QR code, you'll directly go to the website. And yesterday I checked, and we have more than 360 commits in total. What you can find on the GitHub project, just take a look, there's a Gantt chart for how we like to proceed with the project. As I said, there is a process specification, the layout for manual, then we have clearly layout, property and tech files, the different models for simulation, one side for HPTs and for Spectre, for CMOS, and even some other stuff what you have in such a technology. Resistors, SRA caps, and so on. There's support for OpenEMS, so you can have a type of EM simulation. We have the primitive devices, so most transistors and bipolar transistors, USGS, and later I will even explain how we can create a type of pi cells, and finally some was HPT measurement data. That's even quite nice because in that case you can verify, you can run a type of simulation, and you can verify this in the simulator against the measurement data. You can take a look, okay, is the simulation right, or is there maybe a bug either in the model or in the tool can be involved. Yeah. Then we're offering a type of standard cell library. This is still in development, and this is even, I'd like to mention this, a very quite nice example, because last year, I cannot remember exactly which month, there was a hackathon, luckily at ETH Zurich, yeah, and they provided some additional cells during this hackathon for our technology. Quite nice example for collaboration. Then we have SRAM cells. It means not cells that are complete SRAMs. You can use it, for example, 180-bit ARCs are available, and words with 8-bit are available as the SRAM itself. And we have some test structures. Here's an example of the design flow, how we can see or how you can do an analog design. This is the type of basic approach you can see on the right side which tools you need. Xgen, COSCUP, and GSpice, size for simulation, and finally K-layout for layouting and OpenEMS for even simulation. I do not want to go in detail later because it's detail because just recheck the slides if you are interested. Then we have type of digital flow, clearly based on the analog basic PDK. Without the analog basic PDK, you cannot develop the digital standard cells. We are providing digital standard cell library, including IO cells, and we have support for the open road and open name apps. And with the help of that, you can generate digital layouts. Once in the survey you've seen, there was even one in the lower left corner something about tooling, open tool development. Yeah, and what we are doing not in this project is we do not develop complex tools. That's not our approach. What we like to do, we like to enable type of basic flow, and this means we have to have some minor enhancement in bug fixes. Yeah, for example, in the GSpice, some bugs came up, and then we contacted Holger Vogt. You can see in one of the lines. Then there was even some collaboration in COSCUP with Michael Bryanson, and even K-layout. It's not well known. We have direct contact with Matthias Körperlein. This is quite nice. I will explain later why. And even OpenEMS, there is one guy his name is Jan Tauber. The example for the K-layout that I like to give. We providing a K-layout-oriented design flow, and you need parameterizable sets. So it means if you have a CMOS transistor, you like to scale it maybe in this or next or whatever, and finally you need to have a type of physical verification. But main focus is currently on the cell itself. And you can see on the top there's a rectangle and K-layout pi cells, and this is type of layout domain because we have an approach to generate this type of pi cells. Maybe one of you knows Synopsys pi cell studio, and this has an API. And what we are doing in conjunction with help from Matthias Körperlein, we are implementing this API from Synopsys pi cell studio with K-layout. This has the advantage if you have program in PyCell, which can be run in Synopsys or can be used even in, I think, AES supports it, and one very old version of Cadence Virtuoso, that you can directly load the cell and change the properties even in K-layout. It's not required to adapt the PyCell code. You can take exactly the same PyCell code. And from my single source and you can use it in different tools. Thank you. Clearly, so finally maps to the technology itself. In our case, SG32 technology, but we even provide this stuff on GitHub later, so that you can even reuse this in your PDK. If you develop a PDK for your boundaries, then you can take this one. So we started to develop some PyServers. So currently we have roughly 20 certs migrated. So that means the HBTs, the most transistors, resistors, and the searing. So the searing is the prototype of your final device. And we generated the required PyServer classes, and the implementation is currently in progress. So we have some examples ready, and for some specific sets, you need some specific commands and development, and as I said already, in future it will be released to GitHub. This very short slide regarding the teaching itself. We are just right now starting to develop digital certificate design courses. So for that, even you will hopefully hear in the next future more. And then finally some words about the silicon proven IP cores. First, we have developed a standard cell library. We know that this needs some improvements, but finally what you need, you have to establish a type of IP core library. So that someone likes to develop maybe microcontroller, he wants to just use an SPI core, for example, or if you have an LNA as analog design, then maybe you need a bandgap, and there should be a type of IP core library, so you can just use a bandgap, integrate in your device, and you know it's verified. And for that, we are offering free MPW shuttle runs for the open community, and the first one was in May. And in brackets you can see the T566. That is our internal number for the shuttle run. And this is free for designers and developers, and it is funded by the project, by this FND QC funding project. And currently the takeouts that are made via Europractice. First, ETH Zurich with the Iguana or devices, even also Rhein-Main or KIT or Unimils provide first designs. And you can find some designs as mentioned. And the next one is in November 24. Here's a more detailed overview, so you can even see the schedule for the next 2 years, and you can see the area which is available for each shuttle line. And please consider this project funds can be used exclusively to produce chip designs for non-economic activities, so it means for university, for research projects, and so on. And currently we are developing a concept to provide low-cost MPW area, similar like Google Skywalker made. And at the bottom of the slide you can see a type of approach what we have currently, how does it work if you like to provide your design to our fab for the MPW shuttle. One thing about the free shuttle run. Currently it is funded by the German ministry, and so we have some special restrictions. So it means the samples that were produced are HP property. You can rent the devices, so it means there will be a type of official procedure. Maybe you will have to pay $20 or whatever, or even it's free, but there's official contract for renting the devices. Yeah, or hiring. Yeah, what we like to say. Yeah. If you like to get more details, you can even check the link. As you can see, the hiring period might be several years. So that's the idea of what we have. And yeah, maybe it's even possible to have a type of permanent usage of only a few programs. And one very important thing is export and custom regulations for your designs. And finally, the time takeout approach, what we know from Google Skywater, will follow in the future. So maybe this means a type of shared area for a lower price, but this is still in development and details will follow later. Maybe just check our project website from time to time if you are interested. Funding, current state, that is quite nice because the starting point was this large FND project, and now there's even an update which I'd like to give because there's an open source design initiative and it's called Design. And you see there are at least 4 different projects with different topics. So the flow space, for example, is focusing on compilation of library. Aging is very important. If you like to bring your device in the space, then you even have to provide or if you check your design that this will be working 20 years. Yeah. Dimico, this is a pure analog project, so for a 60 gigahertz design, SignHab is focusing on the sound generator currently and even root of trust elements and so on. And the DC Pro is the design challenge. It means really design challenge, for example, for students on security designs. Some advertisements that I like to give. As I said multiple times, we have a BiCMOS technology with the HBTs roughly 350 gigahertz for FT. And this means we have very, very fast write productions. Use a chance, you can use for that to make analog designs, you can create amplifiers, you can create LNAs or whatever, or to have some analog devices for 5G or 6G applications. Yeah, that's quite nice, and this is a big advantage and big difference to the Google Skywater. The Google Skywater, you have only CMOS technology. Yeah. Because I'd like to do this because currently I see that most of the people are using the CMOS part only. I can understand from design point of view because doing the CMOS designs, especially in digital, is much easier than doing the analog stuff, but we even like to push this. Yeah. And I like to close the talk with 3 wishes. The first one is use the PDK and provide us some feedback. The second wish is contribute to the PDK. If you have some idea and you see you have restricted resources because you are one single person and you're not able to join such a quite large project, just contact us and we can get in contact with each other and maybe we can find a trusted project or whatever. Just tell us and we will see you. And third wish, even the project list of this, please contribute to the tools. Yeah. Also tools you can use the designs. Short conclusion of PDK development is ongoing. We are on coordination with the tool improvement to enable the basic flow. We are developing a digital design course and we are supporting the IP core development because we are offering a free HW shuttle and so finally silicon course can be yeah, and further development in different directions will be done so that we support different projects or funded projects. Last but not least, there's acknowledgement thanks to the community, to all the people which are contributing to our project in the last 2 years and the different funding projects. projects. And even finally, I wanted to say thanks to TR611 for sponsoring myself and the traveling costs. Okay, then thank you very much. And now I am open for questions.
Any questions? I guess there is a person from ownership. You want to talk about it? Okay.
First, thanks a lot for the interesting presentation. You mentioned something in the beginning. You said if you have shuttle run or something and there is some space on the corners, you're sometimes squeezing designs in for free. Did I misunderstood, or that's really what you're doing sometimes? So in other words, if I have some kind of design, I bring it to you guys, and you cannot guarantee, but maybe you have free space and you squeeze it on the outside.
On the outside
Of your wafer. Or is it always a real design you need to submit and then it will be released?
can you tell me the slides?
Sorry, that was somewhere in the beginning. But
It's beginning.
Slide here. You just mentioned it. Yes, the next one. Yeah, here. It was not on the slide. You just mentioned it when talking. Sorry.
Okay, if you have a design for the MPW shuttle line, for the free,
Yeah.
there are some certain conditions to put on the free MPW shuttle line. Yeah. We will have a type of coming in check, so we have to check that your design is DSC clean, that you provide type of documentation, and then we will have finally a type of, if there are too many designs, we have to decide, okay, we are taking this design or we taking this design depending on what is provided and what might be the quality of the design. Yeah. That might be the concept for the future.
Okay, good. And then, sorry, I don't have one more question. You said you will provide some digital course for learning this software.
Yeah.
So this course will also teach how to use the tools and everything. I assume. What is your concept? Will it be I need to register with your website to get the course, or you will put it on GitHub?
I think the final idea is to provide this free. I don't know the technical details at the moment. I know that there's something in development, and I'm pretty sure it will be available for free for everyone. Because that's even the idea of the funding project.
Okay, cool. Thank you. Any more questions? Anyone?
So you mentioned timetable, and so I'm just curious about the status between the RHP and timetable. Is there any official timeline about where the real open for everyone timetable will begin? Like in the Q4 or Q3?
It's open for everyone.
It's not open for everyone, but I mean the registration. I mean, because from the far as I know that it is still kind of closed beta test. So is it will it be like the IFA is kind of their style of putting up a register front page and you can just click and.
No, which is currently not. We are still developing of this. If you like, on the website, and you can contact us there. And the website is the GitHub website.
I see. Thanks. Is there any questions? If not, then we have our next speaker.
give you left in the talk.
Hi everyone, my name is Philip and this here is Charlie de Bear, and I'm a PhD at the University of Zurich, so ETH Zurich, and specifically I'm part of the bulk group and Charlie is our mascot. So we can design things like this. That's why one of our headline projects is these many-core cluster systems, like for example Okami. And obviously we also produce research papers, so if you are interested you can go and read them. And the big question is now, how can you design something of this size at a university? And as you can see, this isn't even the only design we have. We have more than 60 chips, I think by now it's like 70 or something, and we continuously produce more. And the key to this success, to being able to take out this many chips, is to leverage open source. So let's start at the beginning. How can we even design a chip? On the left you can see we need some kind of idea, a spark. And on the right we have our goal. We actually want the physical chip in our hands. Now the first thing you usually do is you describe what your chip actually does. And this is done with RTL, which can be any language, say for example, Verilog system, Verilog, VHDL, and so on. And this describes the functionality of your chip. Then you give this description to a tool called a synthesizer, and this will turn the behavioral description, so the describing the function, into a connection of different logic gates. And then you pass this netlist to a backend tool, a place and route tool, and it will turn the logical description of how the different gates are connected into a physical design where the geometry is defined. And then finally, you can take this GDS and send it to a fab, like for example IHB, and sometimes later you get your chip back. Obviously we need some additional data to make this work, and so the fab defines some technology, like for example HB's 130 nanometer technology, and it describes this in a PDK, a process design kit. From that it can then generate a library of standard cells, and the PDK and the library are both used in the tools you see at the bottom to actually design a chip at the end. And then you quite often also have third-party IPs, so you don't want to design everything yourself because that's annoying, so you go to someone else, like for example the Open Hardware Group, and you take some of their designs and integrate it into your design. And obviously, very important, at each step you need to make sure that what you want is actually what you get. And this is done with verification, so simulation, logic equivalence checking, and so on. First, let's look at the RTL. So, as I've said, with our platform, we write quite a lot of RTL. So, for example, we have different cores, we have peripherals, we have interconnects, and we have a whole spectrum of different sizes of the actual project. So, we have from very small single-core systems to these cluster-based multi-core systems in the middle, and then the very large systems, like for example Okami on the right side. And also we have quite a lot of different accelerators for cryptographic functions, for fast Fourier transform, and so on. And everything is open. You can just go on GitHub and clone whatever project you want. You can take the RTL, make it your own. Everything is permissive licensed, and so you can also use this and develop a chip you can actually sell. So let's take a look at one of these chips. For example, here's Mr. Wolf in TSMC 40. As part of this chip, we have this power converter IP from Dolphin. And this has quite a few advantages. We can actually get to use professional IPs that has been pretty well tested and designed by actual professionals, they get to demonstrate that their IP actually works. So they can then point to our chip and say, look, we actually designed something that functions as we expected. And then from that, this was the basis for Greenwave's technology to design their GAP8 and GAP9 microcontrollers. So it is also a win for a startup that can take this as a template and design a product from it. Wait a second. So now obviously, does this chip work? It's not very interesting if you just have a piece of silicon. So let's put it to use. Let's put it on a very small drone. It's about this size. And it's the main microcontroller on this. And then, it's not very important, it has to perform different tasks. Like for example, obstacle avoidance and navigation, environmental exploration, and also object detection. And all these tasks can run at the same time on this one microcontroller thanks to this cluster approach. And obviously it's on a drone, so it has to be energy efficient, and that's also one of our main themes in our group, is to always design energy efficient systems. So in the last 20 years or so, SoCs have become even continuously more complex. So this very large design on the left is now just this tiny speck in the eye of the Kraken chip on the right side. So what used to be a complete and for the time complex chip is now just a very small part of the entire SoC. You can also see this when people develop RTL, so most of the time you hear about this, about the core, but surrounding the core is a complex system, and here interconnects and caches and so on, and you need peripherals to communicate with external stuff. And then on top of that you also have the software component so that you can actually run useful applications. And then in our case we have this whole ecosystem of clusters and accelerators and so on you actually want to use. That's the part we actually want to research. And for that it generates even more software, more compiler support and so on to actually get this to work. And as I said, usually you aren't interested in building this whole system. You want to research some specific topic, or if you are a company, you have some new innovation in one specific part, and you just need SoC around it to demonstrate that this is actually a good approach, the one you have. And this is exactly where this open source silicon approach shines. Because you can have these SoC templates where you pull together designs from other people, and then you can build whatever you want with it, and you can focus on exactly the thing that you develop. And this approach has also worked with industry. So as you can see here, we work with pretty large companies to actually design test chips for them. And again, this is possible because of this permissive licensing scheme, so it's Apache 2.0. It can be used for commercial stuff as well. And other researchers also continue to use our system exactly for this purpose, so that they have a baseline and then they can develop their own stuff on top of it. And again, there are a few small companies involved in this. So now we have this RTL part pretty well, and the next step is to unlock the rest of this design flow so that we can make as much open as possible. And the first limiting factor is this third-party IPs, which you might use at any stage. And depending on how this is licensed, you can't use it. So you actually need to find third-party IPs with this permissive license. And that's exactly what you can use our systems for, and also user practices to actually collect these open source IPs, and obviously there are other people involved there, like again, for example, Open Hardware Group. The next limiting factor is the information we get from the fabs themselves. So the PTK and the standard cell library are usually very closed down, and they are very secretive with this information. So here we need fabs, like for example IHP or Skywater or Global Foundries 180 nanometers process, and we need them to open the technology to actually give us the information we need, and to then design a standard cell library around this information. And the final part are the tools themselves. So here let's first focus on the synthesis tool. And let's first quickly go through what exactly the synthesis tool does. So the synthesis tool is called YOSIS, by the way. And the first step is to elaborate your design. So again, we have a description, a functional description of our design, and we need to turn it into cells and the connection between the cells. Here, YOSIS first converts into a high-level representation of the entire thing, where it uses entire arithmetic operations as cells, and then it can perform optimizations on this stage. Then, in a next step, it can convert this high-level representation into a generic gate representation. So these cells on the right, they are very close to actual standard cells, but they aren't technology dependent. They are just internal cells for YOSIS, so that they can start and actually perform optimizations on a gate level netlist. And then the last step is performed in an included tool called APC, and here the generic gates are then mapped to actual standard gates used in your technology. And in the same step, it also performs a lot of high performance, like leading edge optimizations on this representation. So YOSIS, the tool itself, it is very clearly structured, and it has these passes, which are just different commands that operate on whatever the current representation is, so the high-level generic gate or standard cell. And each pass is implemented more or less in one file in the source code. It has a lot of guides, both for users and also for developers, to show them how they can design their own flows or how they can write their own passes if they want to. And it has quite a few regular contributors from the company managing YOSIS itself, YOSIS HQ, and also other stakeholders, people that actually use the tools, have developers that work exclusively on YOSIS. And for you, the main takeaway should be that in less than a week, if you have some experience with C++, you can learn how this tool works, how the data structures work, and you can actually contribute a meaningful improvement. Either improve some class or write your own. So now we have the synthesis part covered. Now we actually have this netlist, the collection of the different standard cells, and the next tool is the place and route tool. Here we use a tool called Open Route, and the first step in it is to actually define a floor plan. So we need to tell it, this is how big our chip should be. Here on the outside we want our path, so we can actually connect it to the real world. And we have some macros, here are astrams, and we actually need to place them somewhere on our chip. Then the next step, so that's supposed to be, the next step is to plan our power distribution. So we say, we tell it like the positive power rail should be here, the negative power rail should be here, so you connect the macros like this and so on. And next, we actually place all these standard cells from the netlist on our chip, and this is done in two steps. The first one just places them roughly, clusters them together a bit, and then the second step does the detailed placement, so it actually searches for a legal position for the cell to be and puts it there. Then next we actually need to generate a clock tree so that all our registers and so on are clocked. This is a separate task because it's pretty complex routing. And then you get something like the diagram on the right side, like these spreading clock trees. And as a last step, we actually need to route the design. So we actually need to connect all the standard cells with metals. And this is again done in two parts. The first part just plans roughly where the value should go, and then the second one makes this value real and start to fix any violations that might occur. OpenRoad started as a collection of different research tools that are put together into a common flow. So, for example, the global placer was the research tool Replace, the router was FastRoute, and the clock tree generator was Triton CTS. Then they built this open database data structure, which was designed by industry professionals, and they started to integrate all these research tools into one common flow so that users can actually use them very easily. And they also built a lot of supporting infrastructure around it, like for example the GUI and command line interface, different reporting methods, it can collect different metrics internally, act on them and so on. And it also has a plugin system, so people can extend the GUI and so very easily. And again, as you can see, there is a lot more involved to this than just designing the algorithms. If you are somewhat proficient with C++, you can actually go in and help improve the GUI or the command line interface or something else. So now we have the backend tool place and route as well. The last thing is verification. There are a lot of different tools involved in here, and I don't have time to go into all of them. So I just picked my favorite, which is Verilator. It is a Verilog simulation tool. And now, as you can see, we actually have everything so that we can go to our goal and actually tape out real open source chips. And this is currently what we are able to produce. This is a chip called Basilisk. It was taped out in HP's 130 nanometer technology. It is fairly large for this technology, 6 by 5 millimeters roughly. It is not very fast, but that wasn't really the goal. The goal was just to see if we can actually design something like this. And it has more than 1 million gate equivalent. Actually, it has more than 500,000 cells by now. It is a lot more than this 1 million put there. And it has a Linux-capable system on it. So you should be able to take this chip and boot Linux. So as you can see, the open source CTA tools can actually already handle pretty complex designs. So if you remember the one of the graphics at the beginning, this single core, simple systems we have covered. The next step are bigger systems like these cluster systems and so on. So again, Basilisk is, to my knowledge, the first end-to-end open source Linux-capable SoC. And it has a DRAM interface and other peripherals as well. It has a silicon-proven RTL, so we expect this to work. And it is fairly large for open source CDA tools. And during the development of this, we also found quite a few problems in this open source flow, and we started to improve them. So we started with this blue dot at the top right, and towards the lower left is direction of better, so smaller and faster. And we actually went quite a bit, and we are still not where the commercial tools are at the moment, but we are closing this gap. It is getting smaller every day. And this is as well, you can just go to GitHub and run it yourself, but be aware you need a very powerful computer to design the chip. So the benefits of open source are clear to me, and I hope allows easier collaboration between researchers because you are not limited by non-disclosure agreements from the fabs. And other researchers can actually reproduce your results ideally perfectly, so they can check that you have actually done your own work. And then the next thing is the industry also profits. For example, for security applications, this transparent chain of trust so that every step is auditable is important, and it also lowers the initial costs, so startups don't have to spend millions of dollars just to get the tools. And this can also accelerate the speed at which you can develop new things and release new products. And then the last step is education. With this increased accessibility to the tools and without any black boxes, you can check at each step what the tool does. You can actually also enable people to learn how these tools work internally. And you can get people to experiment with the flow and the algorithms used in the EDA tools. So education is actually already gaining quite a bit of momentum, like for example this eFabless chip ignite flow, or also the tiny tape-out flow where for a few $100 you can have one of these very small cells in there and actually have your own small design on a real chip in the end. And on the very right side you can see tiny tape-out also already works on IHB's technology, and it should be available within a year or so on IHB as well. And on our side, we have developed this Croc SoC, which is meant to be a very simple chip for students. So on the left side, you can see there are just the minimum number of things you actually need to get a somewhat functional system. And on the right side, you can see it on a 2 by 2 millimeter chip, so it's not very large. And here the goal was that it was as simple to understand as possible, and so everything is just in one repository, no dependencies and so on. And soon there will also be guides on how to use this. We have students currently working on that. It is designed to be as flexible as possible, so that if you are interested in using this, you can go in and modify whatever part you want. For example, if you want to include your own core, then you can just exchange the core and use your own design. And every step of the flow is exposed, and we are getting there with the documentation that always takes a bit of time. And the last thing is that it is easy to run. It runs on older laptops, it uses less than 4 GB of RAM peak. It runs in a Docker container, so it should work on every operating system. And the main flow is completed with just 4 make commands and I think about 8 script files behind it. And we will actually use this for our ELSI 2 lectures starting next year. And the idea is that each year we take about 4 to 5 student designs and then actually produce them with IHB. So our conclusion is that we use open source because it just works. It allows us to manage complex designs and actually produce very complex chips. It facilitates this industry-academia relationship, which is important because at the end of the day we want that our students can then go and work in the industry and learn real things. It creates auditable designs and you can reproduce our results perfectly. And it can also enable research into new directions because we generate data that was previously not available to researchers. And very important for us is that open source sees no borders. There is no European and Chinese and American open source, and attempts to stop this exchange are stupid and don't make sense. There can, however, be different support for these things. So maybe one country wants to invest more money in it than others. So open source is global, and it can just have more or less support. country. But we shouldn't lock down anything.
I love your remarks.
And obviously, there is still more to come. We have just started using these open source CDA tools, and my PhD is on this subject, so for the next 4 to 5 years, we will continue to push the front of what you can actually design with these chips and with these tools. That's everything.
Before I Q&A, I just want to resonate with your remarks that open source seeks no boundaries, because being positive this kind of track for 4 years, it's always been that, oh, we are American open source, we're Chinese open source, big stuff like that. But open source is borderless. It's just like, I don't know why people are so bonded to this kind of boxes and put themselves into this kind of regulations. It's just so sad.
I think the important part there is that we are not politicians. We don't need to play these games.
Yes, exactly. And we use open source because it works. I'm a software engineer, but the first time that we can do this kind of things is like in 2019, because Evaluus is giving a talk to the Request Summit, and it all sparks me to get involved in this kind of things. And open source works. Yeah. Okay, let's get the Q&A. Is there any questions? Okay, good one.
So may I ask where did you get those macro like SRAM or the other macros you used?
So the SRAMs we currently use are on IHPs, on the PDK, and they are part of it. So there are already a few SRAMs available, and there should be more incoming soon. See?
Okay, back to mine from my side. On our behalf, we have several SRAM sizes available. If you need a certain size, please ask us, then we can check. It might be impossible to generate it. Yeah. Thank you. Any more questions?
Are there any one-on-one course for the open source IC design in your mind?
On the topic of courses, so this project, this one, we are planning to make like a wiki or something where you can actually go through our whole course. So actually go through designing the RTL and also learning how the backend works with step-by-step instructions, exercises, and so on. We are currently working on that. I think it will take about a year or so until that's actually public.
Do you want to ask more questions? Or? Okay. I want to resonate with this question because many of us come from the Department of Computer Science or Electronic Engineering, so we know how to do this. But that's for open source, like when the first time I learned how to program is like in my elementary school, and I randomly ran into a book and read it all through and start programming since then. But for learning how to do the digital design or do the basic things, it's more or less more complicated. And the Professor Chen from Kinman is actually asking this question for his students because somehow you don't just have the right materials to ignite this learning path. It's very slopey. The learning curve is very steep. Yeah. So that's a problem for all of us. And if Christ works, then I really hope to know more about it. Yeah.
And also on this point, we're already in talks with people from other countries to then either translate our course or the EU, a few EU and European universities are working on a similar project. And our goal is that more or less the same exercises and same explanations are available in different languages. So it is actually as easy for students to learn as possible.
Excellent. Any more questions?
I see is the older chip remains, you use the commercial tool, and right now you use open source tools. So do you have a small comparison between these two roles and how the outcome difference?
So comparisons to the commercial tools are always a bit difficult because they don't like it and you don't want to like it. So here, that's also the reason why we just have this cloud for the commercial tools. The commercial tool is somewhere in there. They are fine with like these rough comparisons, but they usually don't like if you actually publish comparative results, and also with respect to the flows, to the commands and so on, they can be quite restrictive on them. So we can't really say more than we are getting there.
By the way, that because for the eBubbles and the Skywire, they have the the template SOC Parallel, and so this crack also in this kind of manner that they will be your user design area, and the hardness SOC is this kind of the same architecture you're using.
So that's actually one thing we want to be different than Parallel. So this is Parallel for everyone. You have this user design area where you can put your own design, but then the path frames, so where the paths are, and a bit of assistance infrastructure is given. So you can design the whole chip however you want. And the goal with Grok is that we just have this minimal infrastructure and pins on the left. These here. And they are given, you can change them. But everything else you can change. You can change the size of this chip, you can change what exactly is in there, you can change the core if you want to, whatever you want. So we want to be as flexible as possible.
Okay, thanks for the explanation. Is there any more questions? Okay, if not, then give a big applause to. Thank you so much. Very. You probably remember correctly that the COSCUP was lost somewhere. Okay. Poor affairs.
and I'm the main dev behind Spazio and COSCUP. And now I will do a demonstration about the experience firing of Azure and British Media. So I will show you the heuristics. My table is with some, here you see some USB hosts, ports, audio outputs, ASM output there. So it will take a bit of time to boot. It's really a start process, and at the same time we can get a little bit more. So let's do this. So here is the serial port, also the serial port and I'm beginning to boot it. And behind you can see some noise. That's the HDMI output of the board. So let's go to the system. Here there is an interface loading the kernel. Here is Linux booting. Now it's switching to the HDMI output. So now Debian is running, so the system D, the services, a bit of time. On this board, now there is quite well.
个声音就是大多数人。哦，这三个都。
对，然后就顶吧，因为其实也不一定要这一台，那这一台就是有一个规模在，所以就用这个这一台包括可能来读取，然后不止可以读取，就是它其实这个这一台。大家都会在上面查阅这个，然后可以从这个那个还是这样的一个形象。对对，但是有很多动画就是这一台都是新的。它这边它其实可以接到的，所以你可以对报上面任何的这一个，然后这边透过这一代的，那这样子只要有 USB。
Our next session will be starting now because we're having trouble with network, so I'm playing the pre-recorded video. The speaker will do the Q&A session on live, and here's the video.
I'm Catapult, and I'm the main test behind Spectacle and COSCUP. And I will do a demonstration about backstory firing and FPGA and multiplayer. So let me show you the FPGA kits, my table. And this is some heads, some USB hosts, ports, audio outputs, HDMI router. So because it takes a bit of time to boot, let's we have a start process, and at the same time we can then talk a bit more about the setup. So let's use this, like this. So here is a serial port that FPGA already used and made into grid. And behind you can see some wax and noise that is there allocated of the board. So let's put the system. Okay, here there is matrix views loading the kernel, here it's Linux booting. Now it's switching to the XMI output. So let me enable this. Okay. So here we are. So now the data is running. There is system D using all the services, so it will take a bit of time. On this board, now there is a quad-core 96 kilobytes of Vector cache. The activate, which you can see now. USB bus support, I can use data for the mouse and keyboard. And through USB bus, there is audio output with 3.5 mm jack. The file system is on an SD card. And the main memory is some DDR3 of 100 megabytes. So the system is based on latex. So latex provides all the peripherals, the DDR3 controller for Lex to run on. There's a password architect debug to load binaries or debug with TP or something like this. And the facilitator is also system that we will again, so the FPGA 37. So it's an old FPGA and on time models. Unfortunately, the slow speed rate so it doesn't really help. But here we are logged in. So let me. Oh yeah, I need to plug my USB to the board. My USB keyboard is still on my desktop. I need to switch it now. Okay, now it has USB. It takes quite a bit of time to log in, and then it seems it's because of system D, because when I log in all the system like Bluetooth or Alpine Linux, it's very fast compared to that. But you should make, in the space, so here I have a folder with a few demonstrations, including a boot script that will start X11. And then start at the scope manager with a few widgets on the front of it. So let's go. So we should see the mouse as well as the terminal, which is what you get if you start with 7. Here we are. And then window maker. So window maker is an old school desktop environment which has an advantage to be quite lightweight and have quite a few basic features. And here we go, 30 second close. And here we have our terminal. And here is the demo. So starting with CPU info. So here we are, Quad-Core, NeoFlash. So NeoFlash takes quite a bit of time, but if you try it on your desktop, you will see if you type it, it still takes like half or a third of a second. So it runs slow, it's normal. So here we are, maybe I can start. Here you can see the CPU occupancy for each floor. I will start on the terminal with HTOP. Here we are. What else? Like this. Can you? Yeah. Here we go. Can you click them? So here we go. I didn't enable the sound because when I run it with Doom, it takes quite a bit more time to start playing to cache all the sound. So let's run it as an MP3 player. MP3, here there is the sound. And one thing I use, and I lost screen space. Go. that's why it's managed on the area. Branch means 4% unused stock network. Doing is not really enough, it's really here we see the number of institution cycles, somebody's really not like that. So, yeah, what about, stop the sound, stop this, and play a video. So, for that, use a player, for instance, with trading machine, where I can play games, right? Yeah, so you see, it could take quite a bit of time to start. The reason is in distribution like the packages are combined a way to use shared objects which come from all the packages. So when you start big application with a lot of dependencies, they tend to have a lot of shared objects to learn at the beginning to those, and that takes a lot of time, like about 30 seconds for one player. But we should get that. Here we go again. So, yeah. So you can see down here the CPU kind of quite busy, but it plays the sounds stay in sync. Okay, that's it. So, and now the slides. Yes. Is COSCUP. Oh yeah, and I will reduce this because it's like very old space. There we go. And full screen. Okay. So, sounds like we take a bit longer than over to one day images, but it's usable. So, yeah, just here a fast recap of what is necessary that we're running down. So it's based on the line for all the verticals. All the barrels, it's mostly LaTeX. There is a quad-core 64-bit 55 with GC extension that's mandatory if you run Debian currently 55. So he have FPU, MNU, Atomic, multiplied by, and CME instruction can be compressed into a 16 format instead of just 2-bit. For FPGAs are constantly unfortunate, but that's the situation right now. There is 250 2 instruction cache and data cache from each CPU are each 16 kilobytes, always. After 7 FPGAs, that would be great. This full SoC use 65,000 megahertz, and there is a few. Here is all the memory current agents. USB, hosts, use the DMA, UC, the DMA, the HDMI directly access to the VRAM. That's how LaTeX is designed right now. And a few other peripherals. I have to give you time, but here the talk is going to explain how to bring up Linux to OpenSPI and Linux and how those things work. There is here this SoC that synced and that link involved process interrupt between CPUs and the peripherals, and you have to run timer and software between CPU. And so, okay, here is the current VEX285 video set, so yeah, it's mostly dedicated for it. It's mostly designed for FPGA, but I guess it could be targeted for executed to display. Another extension I haven't mentioned is BigPipe. It can run Linux, Windows, Debian, as a drive Alpine Linux, TR611, well. And also you can set up it to have multiple issues. The main just use multiple like 2 instructions per cycle, it can be done. It will reduce maximum frequency, it will increase the number of instructions per cycle you can do, the trade that the workload you want to run, you may want to make that on that. There is also kind of a late schedule. That's a concept that you can have a normal early DAU, state 0, the exit state, and you can have a 7 DAU in the same pipeline to execute instructions which will have late dependencies resolution, like if, for instance, you do a memory load, and add something on what was loaded. That's a late dependency because memory load will come late in the pipeline, so you can't run the DAU next cycle load started. Until later that you can do that. So that's one trick of performances which can be enabled. And if you done everything on performances, can be quite high, but I would say it really depends on the workload and how things are compiled. Because multiple CPU which are in order are quite sensitive to how things are compiled and dependencies between instructions. So keep that in mind. So for this demo, it is a single issue with no late schedule required. So the whole project is free and open source. There is no there's no behind. It's really true to the spirit. It also supports the kind of show type. It's rated forms. And then, yeah, now we'll talk a little bit more about CPU architecture to get more performances in the context of other CPUs. So the branch prediction is an important one. We have seen before that it was very perf, only 30% of the branch were mispredicted, which is really not that bad, but it's okay to it's not very hard to predict. But anyway, branch prediction is not really well named, I would say, because it's more than just predicting if a branch will be taken or not taken. There is first, before predicting if a branch is taken or not taken, you first have to predict if the instruction stream you are fetching contains branch instructions. You need your branch prediction to run and before you know what the instructions are, so really early in the pipeline. And to do that, you have to BTP. So the BTP will predict in the instruction stream what part of the instruction stream are branch prediction, branches or call or beta instructions. And it will predict where they branch if they are taken. So that's the BTP. And then, for instance, you have the reshare predictor, which will only be useful for branch to predict if like the branch will be taken or not taken. And I will not go too much into the data here, but that's the main idea. Really early in the pipeline preparation to keep the instruction, keep the CPU pipeline feed with instruction. There is one other thing which is instruction cache prefetcher. So it really depends on the application you're running. If you're running an application which is processing data in a loop all the time, you don't really have issues with instruction cache having too many cache misses. But if you run application in big application in Linux, you have a lot of code that needs to go through, like running, for instance, OpenTV or these kind of things. You start to have the issue that, yeah, CPU is wasting a lot of time on the so-called cache misses. And so to fix that, either you make a really much bigger cache, either you implement some perfecting things. And so in X2, that's a thing called added. When you use string cache, you have a miss. It will trigger a cache refill, that's normal. But this cache refill is non-blocking. I mean, you can have multiple cache refill at the same time and still have requests coming in into the cache refill. That's one thing. You have multiple slots of infinite CPU cache refill. And when you have a cache miss, the professor is also informed that there was a cache miss, and so the current implementation is that when there is a miss, the professor will trigger a prefetch for the next cache line. And then, if, for instance, the CPU executes an instruction on a given memory block, and that memory block appeared to be the one that was used perfectly before, then it will be the trigger to the next cache, trying to stay ahead of the needs. So that's one thing. It's really not a complicated design, but it can already make a quite big difference. So I still rate it as a workload, but sometimes it really make quite a big difference. So, and then we as well at the cache professor, and here are some performance numbers to illustrate how it can be impactful. So when the latest video starts, it does some memory benchmarking, and without the cache professor, write speed is for the CPU running at 1 MHz. The write speed is 168 megabytes per second, which speed is 130 megabytes per second. So when you enable the hardware professor for the cache, you get really a big boost, especially in rate speed, you more than multiply by 3. And then you nearly multiply performance by 4. So, yeah, it can be really impactful. How you translate into a real world scenario, I would say it really depends your use case. For Windows, for instance, it boosts the speed by about 20%, if I remember well, 20% more frames by having a data prefecture. So, and it's not an expensive design to do. And it's a bit like the same for the screen cache. You have the data cache, and you have multiple slots for refilling a cache line with new data. You have multiple slots for infinite write back of dirty cache line you need to move to make space. So yeah, you have to design where you have a non-blocking data cache, and each time the data cache is accessed by the CPU, the professor will get notified, and he will maintain a table of what was the last instruction at that program counter, like it was a load, it was a store, and at which address that memory was stored, what accessing things. Is what was the delta in address between the previous address and the previous one. Like for instance, if you do a memory copy, you may have like 4 bytes offset between each access. Every time 4 bytes, you have a strike of 4 bytes, and you have a score to, for instance, figure out, is that always the case? Is my access that instruction always doing a plus 4 bytes access pattern? So it's really variable, so I can do a lot of professional of that instruction because it's always doing the same. So yeah, you have this kind of structure where you have tables to keep memory of what happened in the past, to take this kind if it's good enough to prefetch some cache line when this things happen. Can be really impactful. And another aspect of the work system is it's memory system. So there is memory currency between all the CPUs and VMA in the system, except with the VMA for some figures. But there is another concept that all the memory interconnects is running out of order. That means if a CPU writes a given address and uses a cycle after several requests to read the same address, you don't know what you will read back because things can exist out of order. So the memory interconnect may first do the read and out of the write if you request things in the other order. But this can seem tricky to learn, to handle, but in practice it's really not that hard to handle, and it has really a lot of great upside, especially when you have an L2 cache. When you have an L2 cache, you have the memory access latency can vary greatly. If you have a cache linked to an L2, memory latency can be like just 5-6 cycle latency. But if it misses the L2 and has to go to the DRAM, you may have, at best case, 2 times associated to the best case, you have 20 cycle latency. More generally, you have 30 cycles, and it can go up to 100 if the DRAM is doing some refresh and semantics. So you really need this kind of memory interconnect being able to work out of order in order to keep things flowing in the system, to not have one L2 cache is holding everybody else behind. And so it is based on types. And yeah, that's it. So looking for contribution if you are interested. Really, it's a big project. I haven't talked really a lot about it, but one of the ideas is really to have very large design space. Here is a Debian design space core, but there will be a lot of room for more simple system. To improve performances, testing, maybe trying to port this kind of system and edit. Here is a repository. There is an issue, the number 1, which is tagged. If you are interested about the roadmap or want to contribute, you can come here and talk, no problem. And here is some documentation about how you can reproduce what I'm reading on the board. If there is something missing, again, come open and the issue. And as well, thanks. It's hard to find good funding for this kind of project, and I would say thanks to another to provide the funding, open source funding. So, thank you, and now the question.
Okay. So, here we're going to call our speaker. Sorry that this is so messed up.
正在尝试联络的人员目前离线，请在读一声后留下讯息。完成时，请挂断电话。
Come on, Charles, you still there? Hello, Charles, can you hear me? Okay, we can hear yourself as well. Do we have any questions here? Okay, I have a question. Finally, there is official RISC-V JTAG. So I'm just curious about how was the decision to transition from your own RISC-V OCD to the official JTAG. Is that what is the design choice?
That's one other thing for simple debug. The Vector custom debug was really good because it was really a lightweight one. But when it was starting to be more advanced debug, yeah, it was really a pain to maintain as well.
I see. So do we have questions here? I think that there's actually a student also developing his own RISC-V core. Do you want to? By the way, though, Charles, is your Debian port official, or did you bootstrap it from the source?
So, what do you mean? I'm not sure to understand exactly what you mean by official. What I did is I built images using a few Debian utilities.
I mean, if I remember correctly, that Debian currently don't have the official image, and
yeah, so it's not. I didn't took I already built image to assemble it. I didn't assemble it.
Oh, you can assemble it yourself. Okay.
Yeah, in case of if you want to use about the things in the next to is there is a doc folder Debian, and here there is all the steps to recreate the image, and it's mostly based around the tool deb strap that allows you to create a Debian file system, and then you put into it and you can use a few things.
I see. Thank you a lot. By the way, can your CPU run Doom now? I mean, there's a student under there. Sorry, I'm trying to make a connection with the audience because we have previous speaker also putting his Linux on his own core, so I'm trying to teach him that because your core, your VexRISC-V can run Doom, so I'm teaching him that maybe his core can run Doom too. Yeah. Is it okay to run Doom?
Haven't tried.
You haven't tried it? You should definitely try it. Anything should run Doom. So I guess there are two students as well. You have been discussing a lot when Charles is talking about cache system. Do you have any prediction or cache system design you want to discuss? No, not really. Okay. Oh, by the way, Charles, I have a board on my hand that this one is the eFabless. Yeah, it actually have a VexRISC-V version 1 from your core. So do you plan to do the ASIC? Or just let someone else to do that?
For Vex 2?
Yeah, for Vex 2.
I'm not planning to do myself an ASIC because I have too much things to maintain and handle. It's too much of a burden. I actually try to stay from this. So I'm trying to not deal myself with too many projects. So if somebody is interested, I can help with making the Vex 2 RISC-V more ASIC ready, maybe with all the shit about RISC-V and memory, something like this. Black box them, but all no, I'm trying to now really shit.
I see. Okay, so I guess currently we have no more questions here. Okay, so very thankfully for your talk that you have been presenting to COSCUP for 3 years. Maybe next time I'll fly to Swiss and get them to you and have a drink with you too. Sorry. And sorry for the network connection this year. It's really beyond my control. Yeah. Okay. Okay. See you. Bye bye.
Thank you.
Our next session will start at 3:30 in the afternoon, so there's plenty of time for rest. And I'm very sorry for the previous session that actually Charles was trying to, all of his demos running on his Vex 2 RISC-V Lattice SoC, including the presentation and the webcam capture, so it's a fully running system, and I'm really sorry that I cannot provide a live stream with you, but just that demo, right? 在当年的时候还没有这么多学术的 RISC-V core 的时候，有一个RISC-V是每一届都会办那个叫 soft core 的竞赛，然后它是2008年就是冠军，然后那个时候是当时市面上唯一有人做这种厉害的 support， 然后有被报在这里，然后这是也是终于看到这个抱歉，等我一下，面就是再包括他就我说他第二版，应该说当时因为他是唯一一颗我们说的 core， 然后那时候他的这台 module 不是走standard 的，就 RISC-V 其实有自己的定义说，比如说 DI 那个全部是的那些 protocol， 就 default problem 有定义，他们那时候是不走的，所以这个其实不能用正规的，因为不能用通用的，然后它其实还蛮包容，刚刚 Hallmark 的分数其实就是都还算，其实不够。然后来32、16、19，现在这个是否有了身体，然后有非常粗细的，还有
在刚才那给我一个看的地方，它上面是不是有可以帮助到那个CPU的安全？这个开关的
安全是说，
听说它的卡带，
它其实是scale base， 它跟那个我前公司Sci-Fi一样是走它自己定了一套 HDL 叫做 Spin HDL， 然后 Spin HDL 是 based on Scala， 就跟 Sci-Fi 的那个 Chisel 类似，对，它有自己定的 HDL， 然后它会透过它自己的活权transcompile to synthesizable 的 Verilog， 然后 synthesizer Verilog 就给它做其他你要做的事，比如说你要走 load 都可以，然后也可以上去可以这样，对。
我觉得这里面有一点最麻烦的是没有脱权，如何去域名的
扣出来，
可能是手机。
它的东西都了解很多，比如说 for a teacher 的 string 要是出来，它本身都传统，就是不管你想要走Xilinx 的那一套，就是它的托，或是你想要走那个就是 open source 的业托的，或者甚至你要走下一次都可以，它都是传统。
他们的彼此之间的那个就是氛围对比的话，其实大家都可以通用嘛，但是会有一点点差异。
你想说的应该是指说，像我们的概念叫做 zero stage loader， 就是你会需要做一些比如 DDI 这些，对，那它有提供，是那每一个 core 基本上它那个 references。跟我最 zero stage flow 的都不太一样，可是就是 RISC-V 有尝试定义一套，就是它有那个没有一个非常明确的一个分界，就是说它有一个概念叫 DSD， 就是你刚刚那些，比如说oscillator 啦，然后什么 DDI 你都要处理好，跟进来后面的那一段分位，就是包含你的发封闭的那些 peripheral 都封装在一层叫做 OpenSBI， 就是那一层是通用。就是从 OpenSI layer 以上，就不 load 到某个阶段之后，就跟86一样，跟 ARM 一样，就是你会有 UEFI， 那 UEFI level 以上的就是Linux RISC-V 其实也有 UEFI， 那只是因为它 UEFI 是个很大的东西，那下来就是像你做 India tracker 该知道 UEFI， 然后先不 load 就某些不 load 以上层都是通用的。不好意思，
我是想问那一块，你刚好像有提到说这一块是算 RISC-V 比较早期就存在的开发版吗？
状况是这样，就是里面的 SOC 叫 Caravel， 然后它的 CPU core 是刚刚那个讲者 就是他现在今天在报叫 Vex 2 RISC-V，那它上一代就是 Vex RISC-V，它就是在这里面，对，这是一个 RISC-V的 core， 然后有 tape out。
所以这个是因为我刚刚是刚好听到你在谈这一块，是这样，主要是它的定位是这整块开发，它是设计这整块。
这只是这个不是这个 demo， 就是说它是一个，就是每一个层面都是 open source， 所以就包含它的就是 CPU core 啦，它的 SoC design peripheral 都是 open source 的 core 去做。那这块定位其实你说就是它基本上没能做太多事，它就只能就简单的比如 UART 的 output 啊 SPI 的一些 device 可以接上来，就是比如说 SPI 不是有一些按钮啊，或者是一些那种 camera 小 LCD， 对，其实这个完全比不上这个正规的。就是什么真的甚至搞不好连 Codex 30多年你都要比它强。它的目的是单纯就是说 we can do it with open source core 而已。对，这张管子叫 Clear CLEAR， 对，你就打 Clear， 然后RISC-V 应该就会查得到。
好，谢谢。
对，他说对吧？回来了。
这是你刚刚讲的。
对，就是pure open source 的 core， 然后加 FPGA， 它上面有那个 OpenMP2 的 fabrics， 就是你知道，就是 FPGA 其实它就是一坨针指标，对，一坨针指标在旁边，然后就放在跟 core 旁边，对，然后就它是把它整在一起这样的。那其实没有特别，就是我刚刚有跟他讲，就是搞不好 Cortex M0 搞都比它厉害，对。但说上去，而且可以猜，因为那个他只是把讯号拉出来，就是他就只是借他的 physical layer， 对，这个其实不会大概200美，对，200美金就去参加那个 donation， 说我要加，对，他说你们有可以来玩看啊，你看拿那个应该是 reset， 帮人 reset button。
200美是这样一个，
是吧？对吧？就200美做这一个出来。
200美做这一个出来。
那个分摊下来的啦。
是指 tape out 吗
？tape out 对。
tape out 它做这样的。
对，因为分摊下来，它这当然是要量去分的。
所以弄出来再挂在别的板子上。
对，这个板子是额外再洗的。对，就跟封测嘛，就是你今天 IC 做出来的时候，其实只会有这个，然后跟一个封测板，就是说，就是因为你晶圆厂出来是裸晶嘛，就说是一个带的，那它会打晶线，就晶是高的那个晶，打到旁边的 I/O pad 上，然后封装起来。那封装起来之后，你要就是正常的 IC 有时候都要做个叫封测，就是封装的测试，就是它会有它的，你当初在 tape out 要回来给它 pattern， 然后去打它，就是说惯性，那我预期它的效会出来是什么？对所以说那些 pattern， 通常就只会有这么一小块，然后可以封这张车，那你回来的时候自己再把它接到你的大老板操作其他东西。
所以回来要自己再接。
对，就是你今天封测厂会给你顶多到这块小的，大的是你要自己上，就是封测厂，因为你今天 IC 的时候你把它做出来，你不知道能不能用，其实完全不符合放去的营业目的。它营业要做有用，也不是叫你做一个非晶圆出来，所以你要提供给他就是 test pattern， 就是说你今天要怎么验它，那晶圆厂做出来之后就会找封装他们的日月光，当然在欧洲没有日月光啦，就把它封装成这样，然后跟这块小板子，然后就开始搭配上去，然后验完说 OK， 这一块是会动的，然后就把它取。
我刚刚说200美是这个 tape out， 那后面你自己在做
这个
接线做这些的那个，
就不止了，对吧？我是指说这一小块的这一块呢，当然你就这才4000是吧？4800游戏 PCBA 那没多少钱啊。对，这个大波一的比我专业，我就不好讲太多。
这也没有自己在画那个。
这是在做赛车的。
那我们有准备在画。
你有在画的要的。
没有在画。他们
现在那些泵啊，对。 了解了解。好，
有这样的课程吗？还是
有啦，我差不多一样。
我们社团有需要会设计的人，但我们好像也没有说，因为课程好像也都是要做什么，然后去查，然后会有一些免费的 YouTube 影片可以看。对，还有一些什么ACD 还是什么的做可以。
可是即使有免费的 YouTube 的影片，可是通常它那些材料之类的也是变成这样。
因为有点麻烦，就是我们有合作的那个印刷。
台湾的话是中国人，
中国人。
然后我就想说，台湾应该没有 PCB 厂的，超少见的，对，还是你要自己洗。
这个就更没有了。我朋友也都是去找中国的。
PCB 会吗？还是我们JCL PCB 我就忘了，反正最大就两家。
他就说最后实验室运过来这样子，其他的把那个条给他们，然后运出来的还要送过来的。还要快100起来。
而且中国那边那些都做一条龙，就是你甚至可以跟他蹦表，帮你都喊好好的，这些 SMD 什么，就是都好了，不用自己按。
它甚至有一个软体是，你可以直接它就是一个设计图，然后你就上，因为每个 IP 你就说你要买这些什么，然后就帮你就做好，然后送给他，然后他就一条帮你直接弄过来。
就是你下面这一块板子，如果你有把各个 file 给他，然后你的 BOM list 给他，你拿回来就是整张已经是好的。对，就是他们那个条龙服务非常非常的，
而且很便宜，
而且很便宜。
所以这个是中国找哪家厂商？
就是我不知道他们是哪一家，不过很多欧美的 open source 的 hardware 其实都是找有一些叫 PCB 位，PCB 要大约10000。对，然后他们那个真的就像他讲，那个软件很方便。
它的设计跟它的商城是整合在一起，就是就可以直接看它有什么东西可以买就买，然后就买就好。是有什么需求要相信？
我是要做教材。
哦，做教材。
哦，不是，我们这个小学。
因为我们还有我们公司有很训练，所以我们其实也是自己训练一些结构起来，然后可以接。
对，你是哪一家的？啊？哦，关于一群哦。
我们遇到比较多应届毕业生，所以我们有时候要从零开始训练。
所以你们有这样的？
因为我们自己弄，就是我们自己拿。我们比如说他刚才讲那个 paper，我们就自己，比如说像找一个可能。就是比如说像我就会想办法写一些东西去训练，就是我可能在写，想办法写东西。然后像他刚刚商场提到那个，我们是有一个叫 COSCUP， 它有一个说4个 make command 的 from RTL to GDS。所以像我们就会找类似这种东西，然后把它拆开来看。
名片吗？
40分钟，还好，一切都 OK。刚刚不好意思放声音。了解，就是因为其实就是慢慢去找他们，然后就个别就寄一封email给他说，就是今年我想再过来啊，然后方便的部分就比较多，像今年就是报道TR611啊，就是我其实你不要常找我，我也是
他们到底可不可以按照规格实做出来，然后可不可以定好全部另外的标准？我觉得不再重蹈覆辙。我在大学毕业了，在标准没有定好，标准。我说标准是什么硬体的实作？我觉得你要验证好，怎样叫标准？
还有7分钟，7 minutes to go。 只有这个桌子。这个桌子跟教室你们是知道的，你可以掌握所有的后面的事情，但是大会我也要求是他们主要讨论，因为他们没关系，我到时候再写一个倾向性的东西给你，先忙，先忙。No, it's okay.
Put a lot of pressure on you.
It's really the last minute. You were the last one, so it's all yours. Yeah, it's okay. Okay, I'll let you do the talking.
Are we going to start?
Just now? Yeah. Yeah, it's ready. It's your time.
All right. Hello, everyone, and welcome. My name is Flo. Konnichiwa, Dacha ni hao, servus da hinten. Today it's my pleasure to be here. Thanks a lot for the invitation, Wayland. Thanks a lot for organizing this at Taiga at National Taiwan University. I am the CEO from Open Hardware, and today I want to give you more overview what is Open Hardware and what we are doing. So, for for today's agenda, I was thinking let's first talk about if you really can use open source chips in commercial applications, and if so, where you could use it. And then after this, I want to give an overview who is the Open Hardware Group and dive a little bit into the course, but also make clear what is Open Hardware Group providing as an added value. So let's start. Can you design a commercial chip and ship it in hundreds of million devices? Yes, you can. I took an example application of a mobile phone. Every one of us has a mobile phone. Now, the main CPU today is still some other CPU architecture, which is not too bad. But the thing is, inside this SoC, you have so many different CPU cores, and a lot of the CPU cores already today RISC-V cores. For example, your Wi-Fi or your Bluetooth or your modem to connect, there are many embedded cores which you're not knowing as an end user, and these are already driven by RISC-V. The memory is another example, or also the touch. These are applications, you don't know it's a RISC-V, you just know I have memory, I can save all my pictures of my dogs, but you don't know which CPU is organizing it inside. So, first of all, RISC-V is already used in commercial applications today. Now, the second example is an SSD controller. Again, an SSD controller inside is quite complicated. There are more than one core inside. You may have something between 2 up to 32 cores. And you have different CPUs like some NAND controller, some SATA controller, or a CPU controller. And these controllers are already today RISC-V. For example, there is a company here in Taiwan, it's called Phison, and Phison is already today shipping with RISC-V controllers for their high-end industrial hard disks. Right, Hello-san? Yes. Okay, but what about open source RISC-V? Can open source be used to ship in a commercial product? Many people say no, but that is wrong. You definitely can use RISC-V to ship in a commercial product. Here I took an example. This is a company in Europe, in French, Dolphin Design. They have a design kit where you can design your own ASICs, so they are a design house. And they are offering this design kit where you can really do different applications like audio connectivity and so on. Inside they have different building blocks like a DSP processor, an audio processor, but also power and so on, additional CPUs. All of this can be RISC-V and they are offering it. So I took the DSP here as an example, and you can see in the DSP you have the RISC-V core. This core is actually coming from the Open Hardware Group. Our core is, by the way, originally coming from ETH Zurich. So that is the RISC-V core here inside. But when you're going to Dolphin today, you get the Dream chip designed by them, and they can put you open source RISC-V inside. So you fully can inspect it, you fully can see what is inside. Now, a lot of people say, come on, it's just a RISC-V core, it's not rocket science, we can easily do it ourselves. And that is true. It's really simple to design a RISC-V core. And there are so many resources on the internet, so that's the great thing. The problem starts when you want to ship in high volume. Making one core, putting one core in a test chip, like our colleagues from Tokugawa University have done, great, no problem. But when you want to ship 1 million, 10 million, hundreds of million, you need to start with different things. You first need to document the core, so other people in your team know what you have done. Other people 2 years later, 5 years later know how to modify it. Once this is done, you need to start verifying the core and actually verification to prove there is no bug inside. That's the most difficult thing when you're designing a SoC. So the verification is very often underrated. But then there is a last thing. RISC-V is an open specification. So there keep coming new additions to the specification. Maybe there are things changed in 1 or 2 years. So if you write your own core, you also will need to keep updating your core. And that's, again, additional work. Update it, and you need to start from the beginning, document it, verify it. So, not easy. Writing the core is easy, getting it into production, that's the difficult part, where you really need to spend a lot of manpower and a lot of time and money. Now the question is, why is the Open Hardware Group here? What is our benefit? What is our mission? If you want to make a RISC-V based design today, you have basically two choices. You can create your own core, like in the right upper corner, the red one. You have fully control of your core, but because of verification, documentation, end-to-end, it is also expensive. You need to have a lot of people. The other chance is you license your IP core from an established vendor. Here in Taiwan, you have Endis Technology in Hsinchu. They are doing a lot of cores, really high-end cores. You have in America, for example, Sci-Fi, and in Europe you would have COSCUP, someone like this. You can license your core. You still can customize it a little bit. Your cost is relatively low because you don't need to invest in all this effort around verification, but also your customization is relatively limited. Now, that is where the Open Hardware Group is coming in, and we are providing a third option. Instead of making your complete own core or licensing a core, you can take one of our industrial-grade flexible RISC-V CPUs, download it from our GitHub repository, and then still modify it as you need. That means you can add custom instructions, you can change the pipeline if you want. You have a lot of flexibility. If you don't want to change anything, just take the core, you take it as it is, you can put it in a SoC. You still need to do some verification, but a lot of Open Hardware members have already done pre-verification, so this task is more easier, so in total, lower costs for you. So basically, Open Hardware is providing a third option to the buy versus make, something using some open source. Now, maybe let me give you an overview of what the Open Hardware Group is providing. We are providing first the RISC-V core. The cores itself are written in Verilog, but more important, they are licensed under the Apache 2.0, a very permissive license. That means you can take the core, you can put it in a commercial product, you can modify the core, you can enhance the core, and you don't need to tell us. But the cool idea about Open Hardware Group is that if you have some cool enhancements or bug fixes, you contribute it back, we all get better together, but you still can do your custom designs. In the core we have 3 different families, CVE2, CVE4, CVA6. Like I said, most of them or all of them actually coming from ETH Zurich in the beginning. And the core itself is nothing without verification. Verification, like I said, super important. Here we are providing an UVM system Verilog 2.0 based framework for verification. It runs with a lot of commercial tools, also with open source tools. However, if you want to put it in a commercial design, most companies are still using one of the 3 big companies for providing EDA tools, so the cores are optimized to work with them. But of course also have recipes for open source like we had previously, OpenLane, Verilator, and so on. The core and the verification is important, but it's nothing without software. So we are also providing the software, some of our members working on the compilers, GCC, LLVM. We just recently finished the upstreaming for both of this, for some DSP extension, which also came from ETH Zurich before, called the PUB DSP extension. Then we are also having different real-time operating systems like ThreadX, but also FreeRTOS, Zephyr, just to name a few. And on top of this, there is also Linux support. Now, documentation we mentioned before is really important. That is another point we are working on. And then last but not least, we also have some very basic hardware On the hardware, we have FPGA images, recipes for FPGAs, and we also did some test chip, which is still in the making as we are speaking. So that is what the Open Hardware Group is providing. Now, who is the Open Hardware Group? Sorry, before we come to the Open Hardware Group, let me give you an overview about the roadmap quickly. The roadmap as we are having it right now. To make it a little more easy comparable, I put the ARM equivalent in the lower corner, and you can see from a very small embedded microcontroller, the CBE2, over an MCU type of controller, CBE4, up to the CBA6, which is an application-ready core. We have a lot of different cores. We are also planning some more high-end cores. One core here I want to mention is the CBW, or also CB Oli. I will introduce this later. It is actually a very cool core because there is a teaching book available teaching how to make a RISC-V design from scratch for an application. RISC-V core who can run Linux, and that is using the CBW. Okay, after the roadmap, now let's talk about who is the Open Hardware Group. We are a global non-profit organization, and our goal is to host and curate high-quality, industrial-grade RISC-V cores. We are a member-driven organization. Our members come from industrial, for example, like Silicon Labs or Thales, big players, but then also from academia, like ETH Zurich, but also from research, like, for example, CMC or Fraunhofer, or someone like ITRI, for example. ITRI is not yet a member, but maybe one time. What we are doing, we develop, verify, and document the cores in line with industry best practice. That means we really want to make this course available for industrial use for commercial products. The most important point is that we are very member-driven. So we're not a normal company where the boss from our company makes a decision. Our decisions are driven by members. I will show you later how this decision process is working. Members in the Open Hardware Group are plenty. You see, for example, ETH Zurich on the upper right, but also companies like Silicon Labs, Espressive, maybe you have heard about them. The Alibaba Group is a member. So we have a diverse set of different members from different countries worldwide. Like before in the talk, open source don't know borders. There are also a lot of academic members. I really like it because a lot of these academic members have great contributions. Harvey Mudd College, for example, but also the University of Minho, who are working on some real-time compilers. So a lot of these people are very active and contributing a lot back or using it for further research. We also have partners in our ecosystem like Synopsys or Cadence who are providing us with licenses, but also other members. Now, if you have this kind of open source, how do you organize collaboration? How do you make sure that people can come and work together? First, when you're having open source, you're enabling a lot of more impossible innovation. You allow people to openly explore, to make their own test chip, to check what is happening if I'm adjusting the branch predictor or something else. But having academic and industrial partner coming together also allows innovation where, for example, some idea from research can transfer more easily into a real project. Now, on the Open Hardware Group, we're a platform that means everyone can come together. There are no NDAs, so don't tell us everything of your secret, but collaborate with other people. Give an abstract idea what you want to do, start making your prototype, and if things work good, then you go with this partner you started, you make your own NDA, you start your own company, or you have it based on this and bring some new ideas into the industry. The open hardware group is organized by task groups. So the main task group is the technical working group. That is really the main where we are making most of the decisions. The technical working group is normally meeting once a month, and then the subtask groups, like the core task group, where we talk about architecture for the RISC-V course, how to enhance existing cores, how to bring new cores. The verification task group, where we actively develop the verification framework, bring in new methodology, but also see what is necessary to get it moving. The software task group, where we are looking for the compilers, but also different operating systems. There are a lot of these working groups. They all report back to the technical working group, which meets once a month. So in this working groups, members attending and members then voting on what is the next project we should do, what is the path we should go, should we implement this new branch predictor, or should we make the new cache system, or maybe both. So that is roughly how the open hardware group is organized. The different task groups are chaired by different members. So here, for example, because the course task group, Ariane Lim from Silicon Labs is currently the chair. Thales is inside, but also many more members. For academic, it's quite nice to have this interaction between industry and academic. I mean, also for Silicon Labs and Thales, obviously, it's very nice to get all this feedback. It just makes things more smooth. The verification task group, I'm jumping a little bit because we don't have enough time for all the details.
It's okay, actually. We can stretch the time a little.
Okay.
It's okay. If you want to go to the details, it's okay.
So I can take some more time. Lucky you, I have no plans tonight, so let me talk for another 3 hours. I just want to give this one example of the verification task group, and that is just the excerpt. So it's not everything, it's just one example. What we are seeing inside is a lot of different things we are using. For example, the core in the middle, of course, but then there is the Google Random Instruction Generator. And for verification, you see Imperas. Imperas is a tool to simulate your core, so you run it on your core and on the Imperas instruction set simulator, and then you compare if you got the same result. Now this Imperas is really great and it's for industrial use, but it also costs license. For people who don't have the money for the license or just want to explore, you also could replace Imperas with Spike, what we are also helping to develop. What I wanted to demonstrate on this is just that you have a lot of different flavors. In industrial, you still need to use third-party commercial tools for quality, for efficiency, for speed, and it's fine. But in the open hardware group, we also make sure that open source tools are compatible and workable with our course. The software task group, here we have Ambercosm and the Alibaba group who are sharing this, and inside the software group we are working on different compilers. Like I said, we recently have upstreamed to LLVM the core awareness, so it knows the open hardware cores, but it also has the XPulp integration, which is this DSP extension, and it also can support native hardware loops, which is basically a custom instruction. Some big European companies have already explored this and found that hardware loops can bring a big benefit in saving overhead from avoiding task switching and other things. QEMU, real-time operating system, and Linux support is ongoing. Linux is of course more than Red Hat. I put Red Hat here because Red Hat is also a member of Open Hardware Group. So they are also promoting the Open Hardware Group and using our course for internal software verification, where they can use an open source core, an industrial grade open source, and verify their apps, make continuous integration, CI, to see that what they are building is running on an actual system. Now, there is also an IDE needed. One of our partners called Ashling from the UK, they ported this Eclipse IDE and made it ready to run with our MCUs. FPGA emulation is underway, so the Nexus board, I think a lot of universities have this. That's one of the cool things in open hardware is that if we are focusing on the RISC-V IP, we bring all these partners together, and that is, for example, something a university could use to say we have an FPGA board, we take the RISC-V core from open hardware, we take the scripts to compile it to the FPGA, and then from Ashland we can use the IDE, for example, based on Eclipse, and get everything together for a teaching course or just for an evaluation course. Now, open hardware, we are working on a tape-out. We are making this kind of IoT microcontroller unit. As you can see on the right side, there is our chip. That is the CVE4 or the CV32E40P chip. Then one of our partners has given us an embedded FPGA. There is also a DMA inside and some of the UARTs. The cool design here actually we have seen already earlier. That is from ETH Zurich, the Arnold design, which we have been reusing here. For us, that is something where we want to prove that our IP is working, which is not really necessary because first it's digital IP, it's relatively easy, but secondly, this chip you're seeing here has over 500 million tape-outs from the course, not from open hardware, but from our members. People who are really putting this in high volume, becoming a member of us, so we necessarily don't need to prove it, but we just thought we are making this chip because it's also good for some of our software guys, like keep developing the compilers. That is helping if you have a real chip and not need to run everything on FPGA, mainly for the timing and things like this. So the dev kit is like here. Like I said, we got, when we taped it out, that was a joint effort between more than 6 partners. So as it happened, if you are organizing a big team, we got some small glitch inside. So we are now making a respin of the chip, which should be available somewhere early next year. Let me give you an overview about the course. I don't want to go too much into detail, just some very high level about the 3 families. Actually 5 with the CV, 4 with the CV volley. But before I go into the course, I want to bring up a term which is the TRL. TRL stands for Technical Readiness Level. In open hardware, but also in a lot of other companies, TRL is used to analyze the quality of the chip or the status of a chip. So for example, when we got the chips or the RISC-V designs in the beginning from ETH Zurich, we classified them as TRL3. The design was done, ETH or platform team made a tape out, the chip was working, maybe some minor issues inside, so we had a proof of concept. But this proof of concept is nothing which you want to bring into production if you're making hundreds of millions of chips. So you need to start to verify it. That's when it moves to TRL4, when you're verifying it somewhere in the middle. And when you're done with this verification, you have no coverage holes inside. Then we are declaring it TRL5, which means the system has no bugs, no coverage holes, nothing. It's ready to put into production. And then actually our members taking it to TRL6, to TRL7, and even to higher qualifications. So this TRL system is very good to have a first impression on the quality of the IP. If you're a hobbyist, TRL3 is really great, it's good, you get a running chip, but if you want to make hundreds of millions, you need to have very good verification, you need to go a little bit higher. Just wanted to throw in this terminology, it's quite useful and widely used in the industry. Now coming to the course, the first core we have is the CVE2. That is a 2-stage in order pipeline. It is really optimized for deeply embedded applications. That is actually coming also from the ETH Zurich. It is also used in the low-risk Open Titan project. It is called IBEX there, really great core. If you don't know low risk, you also should check them out. They do really great stuff, except for root of trust and so on, ready to take designs. Taiwanese company Novotech has made a chip with them. Google is putting them now in Chromebooks, so that is really where open source is used as a root of trust to verify things. And if you want to put it in your own design, welcome to check it out on the Open Hardware Group. The project goal is TRL5. We are currently in TRL4, so it's not fully verified yet. We're expecting to have it fully verified within the next 6 to 8 months. On the GitHub there, you also have a project repo. That means you can check out the project repo. There is a project management inside and everything, which gives you the current status. E4, that is a 4-stage in-order single issue again. What is the cool thing here is that we have different versions. So the version I'm showing here is the version optimized for security, something like, again, a root of trust or so. It has a lot of security extensions inside, and it also has a special extension for custom security. Now, this chip has a few different versions in open hardware. We have one for the security, we have one for IoT applications where the DSP chip is inside, and there is also one version which is made for accelerator-based workloads where you have interface to connect an accelerator quite easily. The next one I want to introduce is the CDA6, a 6-stage in order single issue, again from the ETH Zurich. They called it Ariane Core. We have renamed it to CDA6, Core 5 application 6-stage CPU. Maybe the name is not the easiest one, but kind of tells you about the core. This core we are working now on TRL5. There are some big companies involved, also in Europe. By the way, the European Union has also selected this course as a baseline. So a lot of European companies get money to develop based on this course or to help to verify it, to make it available for other startups in Europe. But however, because it's open source, it will not only benefit Europe, it also can benefit here. It can benefit in America, wherever you want. So that is a great thing in my personal opinion. Now, the last core I want to quickly give an overview today is the CB Volley core, or CBW. It is currently also in TRL4. We are preparing it for TRL5. And this preparations, by the way, that means we are having a weekly call. There is a university driving this right now, so we have a weekly call with our in-house verification expert, where we align on the strategy, what are the next steps to do to verify how to close the last open holes, coverage holes inside. This core also can run Linux. Now the cool thing is that there is a book available about it. The book, you can see a picture here, Digital Design in Computer Architecture, RISC-V edition. There are other editions, but you only are interested in the RISC-V edition. And this book is really teaching how to create a core from scratch. And in the end, when you finish the book, you should have replicated the CB Volley core. Now, some secret I can share with you. There will be a new book, RISC-V System on Chip Design, the same authors, but this time they are making an SoC and are teaching how to make a complete SoC with peripheral. So if you're looking for some teaching, which we had in the beginning, the question how to do this, that could be a good starting point. But also if you want to learn more about RISC-V, I highly recommend to buy the book. I bought myself. It's really great for reading and for getting more information. Okay, that kind of brings me to the end of my presentation. I really hope you are choosing RISC-V from open hardware for your next design, no matter if it's research, if it's a product you want to create. Our products are open for both, and we are having a platform where we're enabling the coexistence or the sharing between industrial and academic institutions. The course itself, fully open course, that means the RTL, but also the verification, plus the documentation. So let's work together, let's create this RISC-V course together, let's create some new innovative things based on RISC-V. That brings me to the end of my presentation. Thank you very much for your attention. If you have any questions, feel free to let me know. And thanks. Any questions? Yes, one question here.
Is there any clear debut date about the new RISC-V SoC book?
No, it's only in end of Q1 next year.
Okay, thank you.
Thank you.
So I see that your core is not provided by well, I think there's a page that I think it's a CDE4. The page that the 32 bits core and the 64 so next page. Yes, I see the 32 bits and 64 bits come from the different provider. One is Zurich and the other is
That is correct. So the Ariane core originally came from ETH Zurich. It was a 64-bit system which you could configure, and the guys at Top Platform team made some really great designs with it. Then we took it to, or we got it donated to the Open Hardware Group, and with our people we started to verify the core, to add some missing points. Now some of our members, like Thales you mentioned, they came and they said, we love the core, it is great, but it is still too big. We make a kind of more embedded design, we don't need 64-bit, we need 32-bit, we have a commercial application which we run in high volume, and so having 64-bit or 32-bit makes a difference in gate count, and if you create millions of chips, this difference is apparently big enough to say we want to scale it down to 32-bit. They also make some other options. They don't need an MMU, for example, so they also remove or make a configuration so you can say compile without MMU. And that's why this core looks like it's coming from Thales. It originally comes from ETH Zurich, but we are working all together to create more versions or more different use cases. That is, by the way, also something very interesting. I heard one gentleman just told me that he said the 64-bit is great. It runs perfectly for accelerators or AI workloads, which is where RISC-V is used massively. But if you want to bring it to more embedded application, even with Linux, you still need to have a 30-bit version of it. So there is now some porting ongoing, and there is a lot of fight on some software mailing lists because they say we don't need 32-bit, we only need 64. Who is using 32 anyway? But these guys are arguing with technical background and say, look, it's a cost question. If we can make it 32-bit, we can save a lot of costs, and for the next years, for an embedded device, 64-bit is overkill, maybe, for some applications. So having this in software support off the shelf, so upstream software support, is very important for them. But again, that's the great thing about the Open Hardware Group. We have a starting point, and then we are developing it, driven in an industrial or commercial direction.
No, I have questions.
One more maybe.
Well, just because I recently noticed that the hypervisor settings officially merged into a CPU6 code base. So, and I think that as I saw the 10x engineer, one of the members of the Pablo Mara group had provided the RISC-V MMU. So, just wondering that will there be more async cloud that will include hypervisors and the IOMU part in the future, or well, just curious about it.
Yeah. So the hypervisor hypervisor part was added recently. That is also partly driven by CILETI, someone like E3, but in France. There is also other groups inside, like again, Thales has a little bit pushing there. So we will see tapeouts of this. The question is if we will see it in commercial products. So, or to put it in another way, we will see it in commercial products, but maybe you cannot buy the CPU off the shelf. So maybe it will be something more embedded, but definitely there will be more tapeouts with these features.
That's good. That's very good here because this one advisor in this out of the year specifically. Like we all know that there are people taping out, and we all know that there are products using those advisors. We can never know exactly who made it and who taped out it. So it's good to know that our group is working on this.
There is maybe one to add quickly something. The hypervisor, also it will most like, maybe it will be available in a chip, I don't know. Maybe a member make an off-the-shelf chip, that would be super cool. So if you want to make a company and want to make an off-the-shelf chip, you're welcome. We are happy to support you. This chip will also be working on an FPGA platform. So we are making an image, you can configure 2, 4, 8 or more chips that will run on the Amazon FPGA cloud. So on the Amazon FPGA to make it more fast, but you also can run it on your own FPGA if you have a big enough FPGA. That means you will be able to test the hypervisor on FPGA at least. And you will have some real products later, but for software development you can test it.
Speaking of the SMP, I believe the SMP part is coming from OpenPython, right? The PITOM, the Purdue University provides the logic of SMP. I'm not really sure, but just curious.
There are many different ways you can choose. We are working currently with Professor Jonathan Balkind. He is now at the UC Santa Barbara University. He came before from Berkeley, where he developed OpenPython. He kind of is the maintainer of OpenPython, and we are using OpenPython as the interconnect for SMT. OpenPython is a directory-based network on chip, basically, with also caching and so on. It can scale from 1 to up to 1,000 cores. So, and that's what we are using for the FPGA image.
I see. Is there any questions from Professor?
Do we have any project for educational purpose? You are composing our course for educational purpose to help our students learn how to design the hardware.
Yeah. Professor Chin, that's a very good question. We don't have a course material right now. We do have the open source hardware, and the CD Volley with the textbook could be a good starting point. But what Philip said before, the ETH Zurich is now developing this teaching on the Croc platform, right? So I think that will be a very good resource. At the Open Hardware Group, we are expecting that people who are using it have some basic knowledge about how to make an SoC design. So it's maybe not the best for teaching students in the beginning. However, if students have some experience, I think it could be a good material. The manual is good just for the beginning teaching, something like a 101 on teaching or making a RISC-V CPU. We don't have at the moment. But the ETH Zurich, I believe, will be good material which can be used.
I wonder if you want to ship the medium or more than 1 million of chip, then I think there will be a requirement for the test and verification at the manufacturing. But I think this was one of the parts that the source tool can accomplish.
Because the tools
like a sketch or something. We don't see any discussion about this.
Yes, I'm not an expert for this. What I know is that we don't have any DFT designed for test in the Open Hardware Group. There are a lot of commercial offers, like Siemens, for example. Siemens is also a member of Open Hardware Group. They have the scan chains and all the insertion tools and everything. For open source, I am not aware that it's available so far. But it's a good point if you really want to produce industrial grade CPUs with fully open source tools, open lane, PDKs, very later in all these things is an important step, but it's not everything. We will need to have much more to also make it testable by third-party test houses in Malaysia, in Italy, in wherever they are based. And that's at the moment a missing point. Okay, thank you.
I have a question about projects of open hardware. I find it that, for example, CA6 is supporting more and more extensions. And does it mean like the verification effort of the open hardware is like bigger and bigger? Because you say about member driven, so it's like member will request for more and more extension. And how do you like manage the bigger effort of verification? The effort is bigger again. How to deal with it?
Yeah, that is a very good question indeed. As we are adding more extensions to our RISC-V course, the verification effort become bigger and bigger, and also the time of verification become more. You need more licenses of the verification tools, you need more CPU power to run it. That all is a lot of additional costs. We are handling this in two ways. So at the Open Hardware Group, the CBA6, for example, we stopped completely verifying it in open hardware. We're still verifying it, but not daily, because it's just too much work. We cannot do this. We are depending on the different members who are adding this. For example, we hear that Thales is adding a 32-bit and also hypervisor. So Thales is maintaining and updating this in the Open Hardware Group, but Thales is running the main verification. So Thales, for example, every week verify all the extensions they have added, and then share in the Open Hardware Group, yes, everything is passed or we have some failure. Now, other people who are adding extension will also verify their part. In Open Hardware Group, we make sure we get all the reporting together and make sure it's covered. Once we will generate a new version of the core, like a stable version, making an official release like 1.0 release or 1.7 or 2.0, then Open Hardware Group will run the verification on our side. But we will not run the daily regression because it's getting more and more complicated and we are also not having the CPU power. So Open Hardware, like I said in the beginning, we are a non-profit organization. We get our money from members who are paying us to be a member and also helping us to verify it. But the money they are paying is not enough to run daily regressions on like in this equipment, for example. So our members will run most of the regression and we are only running it when we have a big release. But a very good question.
Because the board from COSCUP is pressuring me to close this. So if you have more questions, please feel free to ask them, but I need to wrap up the hardware.
So we need to finish because we are kind of late. Thank you very much everyone for joining. It was a pleasure to be here. And also COSCUP was a really nice organization. I'm looking forward for next year. Thank you everyone. Have a good day.
I just need to fix the conversion.